All right, so Yuval will tell us about matrix multiplication. It's a long story also next week.
Yeah, also next week we'll get to the really interesting stuff. So today, today it's just like a first course in logic. No, I'm kidding. It's actually interesting. Okay, so the question that motivates this talk and a few researchers is how fast can we multiply matrices? So why do we care about this question? Well, it's a very basic question, but if you can multiply matrices fast, then you can also do other things. So for example, matrix multiplication is equivalent to computing the inverse of a matrix, so squaring a matrix, doing Gaussian elimination, and computing the determinant. So if you know how to multiply matrices, then you can do other stuff, and it's actually equivalent. They have the same complexity. And you can use matrix multiplication in some algorithms. Some algorithms, the best we know is using matrix multiplication. So for example, transitive closure or all pairs shortest path with no weights. Counting triangles, right? So that's why some people are interested in matrix multiplication. Of course, you can also say that this is a very natural problem, and also, how fast can we multiply matrices? What do you think?
I think it's only one of the most widely used algorithms or problems in practice.
That's true, but in practice, people use the high school matrix multiplication algorithm because it's fastest in practice. So
I'm not sure. It depends on the size of the matrix.
There are some rumors that you can use Strassen's algorithm sometimes. It's not clear whether these rumors are correct. Definitely, all the other algorithms are not practical. So it's, yeah.
So here, are we talking real or complex matrices? Are you allowing for symbolic matrices?
Yeah, so you can do everything over whatever field you want. We're not going to worry about it. If you want, the book, Algebraic Complexity Theory, it worries exactly about these things. Everything has a small k, which is the field, and it's not going to matter for us. All the identities that we worry about, they work over any field. If you do lower bound, it's more important. But for these upper bound, it's OK.
Also, the fact that many people do matrix multiplication, even if they don't use the algorithm sequence, is an important motivation.
Right, yeah. So matrix multiplication is useful. Unfortunately, these fast algorithms aren't as useful as you'd think. But the question itself is useful. Yeah. So how fast can we multiply matrices? So what do you think? How fast can we multiply matrices? N squared. Yeah. So nobody expects n squared, and Ran actually proved that in some models you can't actually do it in n squared. Yeah. Right, n squared log n. But before we can ask or answer this question, we have to explain what we mean by how fast we can multiply matrices. So I'll start by explaining the model. And then we'll give an example of an algorithm in this model, which is Strassen's algorithm. Then we will show that you see Strassen's algorithm, if you have never seen it, it has a very specific form, and we will show that it's actually the most general form of a matrix multiplication algorithm. And we also, part of this is showing how you can eliminate divisions, something which Avi talked about. You'll see it's all very simple. After that, we're going to relate this class of algorithms, bilinear algorithms, to tensor rank, which is a generalization of matrix rank. And then everything will become very, we will stop understanding what's going on, and we will start manipulating symbols, which is always good. The next thing we will do is we will generalize tensor rank to border rank, which is some sort of approximate rank, and show that whatever we can do with the usual tensor rank, we can also do with this approximate rank. After that, we'll have the hallmark of today, the asymptotic sum inequality of Schoenhage, or the Tau theorem, where it has lots of names. And this is really, the basic building block in all matrix multiplication algorithms. If you've ever seen the group theory constructions, then this asymptotic sum inequality, it's like taking a Ritz product. Okay, and finally, hopefully we'll have time, we'll do rectangular matrix multiplication. So while we don't know how to multiply matrices in n squared, all to the n squared, if you're multiplying two matrices and the common index is smaller than the big indices, then you can actually do it in n squared, all to the n squared. So we will also explain that. And that was used by Ryan Williams in his paper separating ACC from NX. Unfortunately, after the first version was published, then Andreas Björklund found another version, which uses dynamic programming instead of matrix multiplication, so it's no longer needed there. But it's still interesting. Okay, so what is the computational model? So Avi actually already explained the model. So it's algebraic circuits. Okay, with gates that we allow are going to be plus, minus, times, and divides, and all of them have in degree 2. Okay, so the inputs, in this case, for matrix multiplication, are the two matrices, Aij and Bij, and so it's a circuit with several outputs. Yeah, so what does an arithmetic circuit look like? So maybe it has a plus gate. Okay, so it's something like this. There are several inputs, several outputs. The inputs can come from whatever field you want to work on. In our case, it's enough to, I guess, everything is going to be rational, or even just an integer, or even just plus minus 1. So we don't have to worry about it. And the circuit has several outputs. Now, it will be nicer to use an equivalent model of straight line programs. So they have the following instructions. So you have instructions like this. So here C is any constant. You have this instruction. Here, this is just, it could be any input. And we have these instructions. Okay, and in the end, we want to have the output in the correct variables. Okay, and the complexity is the number of instructions in this program. And it's the same as the number of gates in this model. Okay, so the complexity of matrix multiplication, I will define it formally. So it's CMM of n, which is the shortest, well, size of shortest program. Multiplying two n by n matrices. Okay. Now there's a slight mess here with division. So I asked Avi last week, what about division by 0? So what happens if the program tries to divide by 0? Do we jump off the roof, or what happens? We have to decide. So we somehow want to forbid division by 0. And there's several ways of doing it, but for us it will be enough just to insist that whatever the inputs are, we never divide by 0. So you can ask, if so, then why would we divide at all? But we can say divide by 1 plus x squared. That will always be fine if we're working over the reals. Yeah, so if it's not an algebraically closed field, then we can divide. If you insist on working over the complex numbers, then you probably want to say, if I'm not in this neighborhood, then everything is fine. We'll have to come up with some excuse. Right, but for the normal form, we will actually handle division, and we will have to worry about it. It's some sort of mess that we don't want to worry about. So if you're worried about, then just forget it. Yeah. Okay, so now we're going to define the exponent of matrix multiplication, and this is actually, well, it's motivated by Strassen's algorithm, but I'll define it first anyhow. So this is the exponent of matrix multiplication. So omega is the infimum for all alpha, such that CMM of n is order n to the alpha, also the infimum of alpha. Okay, so it's the infimum for all alpha such that we can multiply two n by n matrices with n to the order n to the alpha. Okay, now in many papers you will see here a minimum, but we actually don't expect the minimum to be achieved. So don't do it in your papers. No, even if it's 2, you don't expect it to be achieved because I'm not allowing any logarithmic vectors here. Yeah. And we'll actually see that for the methods we consider here, then all the methods can always be improved slightly. So whenever we give bound on omega, they're actually going to be omega is strictly less than something. So the methods we consider here, they can never achieve a minimum, even if there is one. Okay, so now it's time to take your printout and look at Strassen's algorithm. So this is from the 60s, I think. How's this one? Is this good? Just for variety. Yeah, so who is this guy Strassen? So he did a lot of things in algebraic complexity theory. So it's not only known only for Strassen's algorithm. Yeah, is he still with us?
He's still with us, but
Yeah.
it's about 8 years.
Yeah, so but that's why he's famous for us. Yeah, so I won't write everything here, but just like the general form. Okay, so what's going on here? So this is, so I only printed 10 of them, so you can sit tighter to each other, closer to each other, and share them. And this is to incentivize you to come earlier to the talks. Yeah, so this is an algorithm to multiply two by two matrices. Okay, and the way the algorithm works is you compute some linear combinations of the A matrix, so the 7 things listed here, and some linear combination of the B matrices, and then you do these multiplications, and then you do these further linear combinations of these products. Okay, I don't know how Strassen came up with it, but people later showed that this is essentially the only way to do it, to multiply two by two matrices with only 7 multiplications. There is some kind of systematic way of developing it in the book, Algebraic Complexity Theory, which you can only discover once you've seen this algorithm. But yeah, so Strassen's algorithm you can multiply two by two matrices with what we call 7 essential multiplications. That's the phrase that is used in really all literature.
I also don't know how he came up with it, but he was influenced by Karatsuba's algorithm for multiplying integers, which
Right.
is also recursive and does something you don't expect, adding things that don't show up later.
Yeah, so I don't know which was first, but you can multiply.
Karatsuba was first,
Yeah.
but it's much simpler.
Yeah, so Karatsuba is like multiplying two complex numbers with only 3 multiplications. That's like the easier case, and yeah. Okay, so Strassen's algorithm gives you a way to multiply two by two matrices with using, if you actually count the number of operations here, it's probably going to be worse than the high school algorithm. So the advantage of this algorithm is you can multiply large matrices using only a small number of operations. So what we're going to show now is that So we have all this algorithm and all this mess, all these linear combinations, but we show that actually the only thing that we need to care about is the number of these essential multiplications. Okay, so let's give the general form of Strassen's algorithm. So this will be a procedure of Strassen. It will get two matrices A and B, and it will output the product. And it's going to be it's very similar. So we write. So we assume that the dimension of A is some power of 2. If not, you can always embed it. So we decompose the matrices in our mind this way. And now we just compute whatever was written there. Okay, so I imagine you've seen it already, but the idea is we take the matrices A and B, which we assume the dimension is a power of 2, and we decompose them into four quadrants. So we decompose each dimension into 2 halves. And then we just follow exactly the same algorithm. And in the end, we get, but now everything is done with matrices. And these multiplications are done by invoking the algorithm recursively. In the end, we just will put everything together and output the matrix.
This is why it's important that this algorithm for 2 by 2 are still the non-trivial.
Yeah, but we'll actually see that yeah, it's often stressed as a very important component of Strassen's algorithm. But when we do the normal form, we will see that it actually comes out sort of naturally. Yeah.
Why are those multiplications called essential multiplications? I mean, it's just 7 multiplications period, right?
Right, but you could imagine that there were some coefficients here, and you had to multiply by scalars. Or,
oh, I see.
Yeah. So we will see that these essential multiplications are actually tens of rank. So we're not there yet. No, but you're right that here there are actually no other multiplications. Okay, so now what is the time complexity of Strassen's algorithm? So we'll denote T to the 2n is the number of arithmetic operations that this algorithm Strassen uses. So let's see. So we need to compute these linear combinations. Okay, so this takes us time order 4 to the n. Okay, then we invoke the algorithm 7 times on matrices which are a bit smaller. And then we have to combine them. So we do some more order 4 to the n work. Okay, and now if you solve this recurrence using the master theorem or using whatever other technique you wish, then you see that the solution is going to be 2 to the n to the log 2 of 7. And this log 2 of 7 is roughly 2.81, and it's definitely smaller than 3. Okay, so this is a pretty simple argument. So what we're doing here, when we're talking about the complexity, we need to consider all the operations, additions, subtractions, and there seem to be many of them, and it seems like it's going to make a difference, but it actually doesn't make a difference. If you actually do the calculation, then the only thing that makes a difference is how many multiplications we're doing here. Okay, so this gives us an algorithm with an exponent of 2.81. So you can say that omega is at most 2.81. Okay, so now we're still in the 60s. I think it was 69, so almost in the 70s. Okay, so this is Strassen's, yeah.
Why can't this method actually help obtain minimum? Or this method?
Yeah, so I'll mention it later.
Oh, okay.
Any other questions? Okay, so an algorithm of this form is called the bilinear algorithm. So what's a bilinear algorithm? So it has the following form. We have M1, it's some linear combination of entries of A times linear combination of entries of B, and we have several of them. And then we compute the output. So each Cij is a linear combination of the values mt, so m1 to mt. Okay, so in the case of Strassen's algorithm, then t was 7. Now we can generalize this. So let's say given a bilinear algorithm for multiplying n by n matrices with t essential multiplications, then omega is at most log n of t, or which is the same, n to the omega is at most t. Okay, so this is just generalizing this recursive argument. Okay, so now the question is sort of why we're interested in these bilinear algorithms. So here we have this nice normal form theorem of Strassen. So we will show in a bit. So maybe before that, we'll call T will be the bilinear complexity of an algorithm, the bilinear algorithm. Okay, so given an algorithm with complexity, algorithm for multiplying two matrices with complexity T, there is a bilinear algorithm with bilinear complexity most 2t. Okay, and this has the following implication. So
Is this true over GF2?
yeah, I think so. We'll see. We'll see the proof, and then we can see if it works over any field. Yeah. So now we can define the exponent, the bilinear exponent of matrix multiplication. So omega prime is the infimum over alpha, such that let's call the, so this is the minimum bilinear complexity for multiplying to n by n matrices. So we can define omega prime, or let's say omega bilinear. So infimum over alpha, such that the bilinear complexity of n is order n to the alpha, or which is the same. It's the infimum over alpha such that true for large enough. And what we're going to show now is that omega BL and omega are the same. It's the same exponent. And this is what shows us that we can restrict ourselves to only bilinear algorithms. Okay, so claim omega equals omega BL. So part 1, omega BL is at most omega. And this follows just from the theorem. And the other direction, that omega is at most omega BL, this follows from what was written there. So from this recursive construction. So from the bound n to the omega is at most omega BL of n.
Second omega to
Sorry,
the
right. Yeah. Okay, so if this thing is at most n to the alpha, then omega is at most alpha. Okay, does this seem reasonable? Yes, no? Right. So now we'll prove the theorem, and you'll see that the proof is pretty easy. It's as surprising as it is easy. Well, let's see. Let's see where it breaks. Oh, so you're saying you can improve it from 2t to t?
Yeah, you never need to do anything non-bilinear if you're over
Okay, no, that's true. But the reason we get 2t is because here it's linear combination only of A and only of B. Whereas if you want to get t. Yeah, so you can get t if you allow yourself linear combination of A and B on both sides. Okay, maybe you can improve it. Then Avi will show us how to improve it.
It doesn't matter.
Yeah, it doesn't matter, but I'm interested, so Avi will show us how to improve it. So the idea is, so we can consider each expression occurring in our program. We can expand it. We can consider its homogeneous parts. So for each expression t in our program, so we're starting with some straight line program, and we're going to turn it into a bilinear algorithm. So that's the program. So for each expression t in our program, we can write we can decompose it into its homogeneous components. So what is this t0? It's the constant part, the part that doesn't have any variables. Okay, so I should say, because we have divisions, if we didn't have divisions, then each expression is some polynomial in the inputs. Because we have division, we have to expand it into some power series. Okay, so imagine we expanded everything into some power series, and now we can look at the homogeneous part. So this is the part where there are no variables. That's where the variables appear in degree 1. Here they appear in degree 2, and so on. Okay, so let's see how we can maintain this form. So we had this, and we had this. So here C is a constant from our field. Here X is an actual variable. And we had this, and this, and this. Well, actually, so that I don't get confused, we'll do it this way. Okay, and now we're going to show, well, we're going to come up with some shadow program to compute all these homogeneous parts, and then we will reason about them. We'll say what they actually look like. So here, because C is constant, then T0 is C, and everything else is 0. Here it's only the one part which is interesting. Okay, now what's happening here? What is T0? Right, so I heard the correct answer. It's not 0, so we're adding two arbitrary expressions. Okay, so again, so these Rs and T, all of them, we think of them as power series in all the variables. And T0 is just the constant part, and T1 is the part with degree 1. And so we just add them. Okay, now to test your understanding, now we can try to do multiplication. So how can we get a coefficient of degree 0? We need to multiply 0 by 0. So now how can we get the coefficient of degree 1? Right. Okay, and here we have a few more possibilities. Okay, and so I have to move this. So now we're going to do the interesting part. We're going to eliminate divisions. And we're going to do it just by solving the equations. So if you can see, this is the inverse of this. So just do it so I don't make any mistakes. So what is R of 0? It's T of 0 over S of 0. We're dividing by something. It could be a division by 0, but we'll get to it soon. R of 1, so this is T of 1 minus R0 S of 1 over S of 0. Yeah, so I only wrote the first three terms, but you can do it in general, and that's how you eliminate division in general. Now, there's a slight problem here because we're dividing by this S of 0. So first of all, why in general are we eliminating divisions? Because this S of 0 is by definition a constant. So dividing by a constant is the same as multiplying by a constant. But there's never any need to divide by one variable by another. Okay, so now why can we divide by S of 0? How do we know that S of 0 is not 0? That's this mess about when are we allowed to divide. So if the matrices that we were multiplying were all 0, then, well, S would have been equal to S0. So if this multiplication works in the case where the matrices are 0, then it has to work also here. This is the excuse why you can do that. But in general, why would you need divisions? It seems incredulous. Okay, so why did we do all these things? Because when we look at the output, then each Tij, so it's actually homogeneous of degree 2. So we only need to look at the 2 part of Cij. This is why we did all this mess. Yeah, so the observation here is that Cij, this is some element of the output matrix, is equal to the 2 part of Cij. Okay, so we never actually have to look at anything other than, well, anything of higher degree. Now there's some more observations. So T of 0 is always constant. That's by definition. Now T of 1 is always a linear combination of the inputs. Okay, and how do we know that? We just go over all these operations and we see that they all conserve this property. And for T2, so it's always a linear combination of products R1 times S1 for Rs appearing in a statement U gets R times S, or U gets R over S, or U gets S over R. Okay, so what's happening here? So the 0 part is just constant, doesn't depend on the inputs. The 1 part is just linear combinations of inputs. Now what about the 2 parts? So it's some linear combination of products of 1 parts. Everything else is just, so because if you look here, then we have this new component, which is R1, S1. And everything here, it's already, we know that it's also some linear combination of R1, S1s. Okay, so you can prove this by induction. Whenever there is some multiplication or division statement, then there's a new quadratic factor that arises, but everything is really just a linear combination of these factors. Okay, so using this, we almost immediately get what we want. So we get from this, we get a bilinear prime algorithm. So it's going to look like M1 gets some linear combination R1 times S1. Where T is the number of multiplication or division statements in the original program. And each output is some linear combination of M1 to MT. Okay, so for each original multiplication or division instruction, then we will have one of these instructions here. And then for each of the outputs, we will just take some linear combinations of these instructions. Okay, so this is not quite a bilinear algorithm as we defined it. It's morally a bilinear algorithm, but if you look closely, then here, these R1 and S1 I didn't say, but these are just arbitrary linear combinations of the inputs. And we wanted to separate the inputs. We wanted to separate them into a linear combination of A times a linear combination of B. And the reason this was really important for us is so we can do this Strassen algorithm trick. Okay, so what do we do? How do we turn this into an actual bilinear algorithm?
You break each one to the
Right.
parts and forget and just do the parts again.
Right. So if you write, say, R1 is A1 plus B1, and S1. So this is the A part, this is the B part. And here S1 is the, say, capital A1 plus capital B1. Then R1, S1 is A1, A1 plus A1, B1 plus B1, A1 plus B1, B1. Okay, so we can break up each of these into 4 multiplications. Okay, so if you allow me to multiply everything by 4, then I can turn it into an actual bilinear algorithm. Well, actually not 4, but 2. So we have these parts, okay, which we don't really need, because if you look at the output, it doesn't actually have these non-mixed quadratic coefficients. So all we really need is these parts. So if we just forget about these parts, then the output is going to be the same. Okay, so we break up every such multiplication into 2 multiplications, and then everything works. Okay, that's where we got the factor 2. If you can use bilinear prime algorithm, then there's no factor 2. Now, do you see anything here which doesn't work?
No, it's too easy because of this.
Yeah.
But my comment about the field is that there is always a confusion when you dealing with arithmetic structures whether you are computing the function or the polynomial. You are computing the polynomial, and then the field doesn't matter. But since you are computing the polynomial, the issue of division by 0 is not it doesn't matter, because division by 0 in the formal polynomial setting is only when this thing you are dividing by is identically 0, which you will never compute in a minimal algorithm. So then there is no.
Okay, so
in the formal setting, usually, so you read that the right model is arithmetic model, but when people study matrix multiplication, they usually talk about the function matrix multiplication. So one has to watch out for we are computing the polynomials, we are doing the formal bilinear polynomials with the input there.
Okay, so now I see your point, and it also works over a field of characteristic 0, where you don't have any of these identities. Yeah, so the comment was that over the GF2 you have x squared equals x. So all of this just breaks. But if the field is characteristic 0, then everything works. Yeah, so maybe you can do better for GF2. I don't know if anybody tried to.
There are real things that happen with these identities, not in the context of matrix multiplication, but there are situations where you can take advantage of the identity and size relative to the size.
Yeah, so it might be that you can multiply binary matrices faster.
So when you say all this breaks, you just mean in terms of if you're thinking of these algorithms computing matrix multiplication as a function, right? But
Oh no, just this normal form breaks. So this breaks. This is not true for. The algorithms are going to work. It's just this transformation that allows us, so to speak, to look at only bilinear algorithms. Okay, so the next point in the list there. Yeah.
So instead of here for bilinear form, and there was nothing on matrix multiplication, right? You gave a canonical way to compute a bilinear form.
Yeah.
So a similar theorem, does a similar theorem hold good for like multilinear forms? That you can always split it?
Absolutely. There's a set proof.
Yeah. This is true for any bilinear form. Every bilinear homogeneous form, you can do this. Yeah, multilinear you get even better. If you want to do things in total generality, you can read the book. It has lots of. Yeah.
But this form, the normal form by x would work for any finite graph, I see.
Yeah. So by if the curve is 0, then.
It's not just characteristic 2.
Yeah.
You just have to decide, you just have to decide whether you do the arithmetic thing or the function.
You might also have seen that actually all these algorithms work for semi-rings. So the correct generalization is sort of different.
Are you saying that so the division elimination breaks?
No, the division elimination, it should be fine if you, depending on your semantics of when it is okay to divide. But the idea there is that when you divide, then you just get these power series, and you can always just compute the first few coefficients. And when you do this, you never have to use division, because when you solve these equations, you only divide by constants. So that's how, in general, if the result is a polynomial, then you never actually have to divide up to some. You lose some constants, but. Okay. Yeah, and also sometimes people are worried about the growth of the coefficients. So if you do it this way, then they never really grow too much, maybe. Okay, so now we have this nice bilinear form, and we're going to show that bilinear algorithms are actually the same as tensor rank. Okay, so you may have heard of tensor rank. When we get to that point, I'll explain what's tensor rank and why we call it rank. And then I explain why it's useful. So let's write our bilinear algorithm again. So we had m1 is equal to alpha 1 times beta 1 all the way up to mt, which is equal to alpha t times beta t. So here alpha I is just a linear combination of entries of the A matrix. Okay, and we have the ijth output is some linear combination gamma t ij mt. Okay, and this has to be equal to sum over k of aik bkj. Okay, now we'll define gamma t to be equal to sum of gamma ij t cij. And the cij here there are just some formal variables. Okay, so now we're going to do some formal manipulations, some like 18th century formal manipulations. So what is the sum of alpha t beta t gamma t? So this is sum alpha t beta t sum. Well, let's put these two sums together. Of gamma t ij cij. Now, what's the coefficient of cij here? So, well, we have this property. So we have sum of gamma t ij alpha t beta t is equal to this thing. So it's this part. So this is sum of cij, well, aik bkj cij. Okay, so what was happening here? I think this should be right. Doesn't matter, but
The tensor will actually have them in cyclic order.
it doesn't matter. We can we won't care about yeah. Yeah, so we're just reversing the order of summation or something. Okay, so
What are those gammas again?
so these are the coefficients. Each output is some linear combination of these multiplications, these products. So these are just the coefficients. And now I'm carrying the indices.
Okay.
And some of them are covariant, some of them are contravariant, and I'm putting them together in some way.
What does it mean, the ijth output?
Yeah, so this is like the Cij, what gets put into Cij, but I wanted to use Cij for something else, so I don't confuse you.
Yeah, but what t means here?
Oh, so T is the number of essential multiplications.
We also used it as the index for summation, which is probably
Yeah.
Okay.
Oh, sorry, yeah. That's very confusing of me. So let's call it capital T. Sorry, yeah. Okay, so we were doing some formal manipulations. So we took sum of alpha t, beta t, gamma t, and then we opened, well, gamma t. That's the definition of gamma t. And now if you sum this over all small t, then you get the ijth output, which is sum of aik bkj. Yeah, so there are lots of sums here, and I'm switching them around, and you're not noticing, so that I don't make any silly mistakes, but we're just changing some orders of summations. Okay, now I want you to think of this identity as some sort of formal identity. So here alpha t is the linear combination of the aij's, beta t is some linear combination of the bij's, and gamma t is some linear combination of the cij's. And when you put them all together, you get this thing.
So it should really write JI. So it's a matter of hand.
Okay, so we'll soon see that we'll actually, yeah. We don't care about order, so if you prefer it this way. Yeah, you're right, this is more symmetric. Yeah. Yeah, it's actually, that's going to be easier for us.
Natural tensor, you don't
Yeah.
These are the triangles in the graph.
Okay, so I claim that this representation is similar to matrix rank, and let me explain myself. And then,
So, Yuval, I
yeah.
just want to say, for anybody who didn't like or didn't follow this formal manipulation, the picture is really, really simple. Let me just draw it. What happens in a bilinear algorithm, here is the A part and here is the B part, and there are all these multiplication gates happening here. And each of them takes some linear combination of A and multiplies it by some linear combination of B. And then here is a C part which takes some linear combination of C. So but you should look at so we have here for every multiplication gate what linear combination of A it is, what linear combination of B it is, and you can just with the same coefficient see that it is affecting C by a linear combination. So rather than thinking of these as inputs and these as outputs, you can think of these as inputs also. And what you are computing, the same circuit, you just flip them, and the same circuit computes the sum of whatever happens in this multiplication gate, which now multiplies some A's, some B's, and some C's. And that's exactly what's written here. I mean, it's just a picture of the identity. So you can turn a bilinear algorithm which goes this way into a trilinear algorithm which is computing this form, this tensor.
So what gates compute this summation, the middle ones?
The middle one, it's
Yeah.
the sum of the multiplication gates, but now you multiply the A's, the B's, and
Like you take this and you move it here.
this is the sum in the top, the sum on the top.
Yeah.
Where is the summation? What gate gives me?
So there's these so what the diagram does, it computes some linear combinations of A's and of B's, and then it spreads them around to the output matrix. So it goes the other way. So we have two matrices have A and B function as inputs, and one of them functions as output. But otherwise, it's always the same thing. We're taking some linear combination. So this is a way of packing the information. And what Avi says is that you can also think of carrying the indexes around. So you can switch inputs and outputs. And we're actually going to do it because we're going to rotate the tensors soon. Yeah, so maybe I'll explain how this is the same as matrix rank, and then you'll have some more data points to compare to. Yeah, so now let's do the same for matrices. So let's say Dij is a matrix, is an n by n matrix. Okay, so we can encode it as D is sum of Dij xi yj. So you can think of this as formal variables, or you can think of them as some basis of the column space, row space, and column space. And if you think of them this way, then this here is the outer product. Okay, if you really like fancy terms, then this is some tensor product, whatever. And now we'll do the same sort of decomposition. Okay, so this is similar to what was happening there. So let's look at this thing. I claim that this shows that the column rank of the matrix is at most capital T. So what's happening here, these things, there are some columns. Okay, so each of these, for each t, each small t, this encodes some column. And here for each j, we take some linear combination of these columns to get the column j. Okay, so this is a way, this is some basis for the column space, and this shows that you can represent every column in this matrix using this column basis. Okay, so this is one way of looking at this identity. Okay, again, so if you look at the coefficient of yj is the jth column, then it's a linear combination of these columns. So these things, the running index here is row, so this is a column vector. Okay, so so you can see that the smallest capital T that you can achieve is exactly the column rank of this matrix. And it's also exactly the row rank of this matrix if you look at the indices in the opposite order. So this shows that column rank is equal to row rank, which is quite a deep statement, actually, I think. Yeah, and both are equal to this tensor rank, which is the smallest capital T, such that you can decompose your matrix into a sum of rank 1 tensors, where rank 1 tensor is just a linear combination of x's times the linear combination of y's. Okay, so it's the same thing that is happening here. Only here there's it's a 3-dimensional tensor. It has 3 indices. Okay, we'll see later that tensor rank is not as nice as matrix rank. Well, it's NP complete, and there are other problems with tensors that don't happen with matrices. Yeah, so what this shows that this bilinear complexity of matrix multiplication is exactly the same as tensor rank of some tensor. So you think of this thing, so you can think of it as a 3-dimensional object which has ones exactly in the places ik, kj, ji. Okay, so you can think of it as a 0, 1 tensor. So we will denote this by n, n, n. Okay, and more generally, NMP is this thing. Okay, so this represents multiplying an n by m matrix by an m by p matrix to get an n by p matrix. Okay, so the bilinear complexity of multiplying 2 n by n matrices is exactly the same as the rank of this tensor n and n. So the rank will be denoted by r. Okay, so now we can state the theorem that we proved earlier. So n to the omega is at most the tensor rank of the tensor n, n, n. Okay, so this is one in the sequence of formulas relating omega to rank of something. Okay, so this is just the same as this argument with the Strassen. You do some recursive construction, and if you see what we actually did there, then this was the bilinear complexity of the bilinear algorithm for multiplying 2 n by n matrices, and this is exactly the bound that we got. Okay, so this is a succinct way of stating it.
And the equality goes to the limit, right? Like if you let n go to infinity, these two terms are equal until they know.
Yeah, yeah.
This is the only way to, like in normal form, there's no way to.
Well, but only omega is an infimum, so with this caveat, yeah.
Maybe it's worthwhile saying that the size of this tensor, of the dimension, is mn by
Yeah, right.
because not one may think that it's mn.
Yeah, this is very confusing because we actually have here 6 indices, so you can also think of it as a order 6 tensor if you really want. So the matrix A is n by m, the matrix B is n by p, and the matrix C is n by p. And what we do is we squish each of the matrices into some vector space. So the dimensions are nm, np, and np.
The initial, the simple tensor mn is just n squared by n squared.
Right. Okay, so now before we take the break, I'm going to explain to you why it's so useful to have these tensors in mind. Okay, so our first claim is the rank of NMP is the same as the rank of, say, MNP, or any other permutation of the 6 3 indices, so any of the 6 permutations. So why is that? That's a bit confusing. So NMP is the sum. Right. So let's see if we can do it without making any mistakes. Okay, so now we're going to switch the A's and B's. Okay, the rank is going to be the same because you can also switch them in the rank decomposition. So this is not equal to so it's BKJ AIK CJI. And now there's some way of switching the indices so that we actually get a matrix multiplication tensor. So if we place this by B prime JK, and this by A prime KI, and this by C prime IJ, then we get exactly MNP.
But if you look at this picture, you don't need to do the calculation, because once you
Yeah,
have
yeah.
such a trilinear circuit for the tensor, you can take any two of them to be inputs and the third to be output, and you get the bilinear
That's true.
linear circuit to compute the appropriate product.
So in
all
this,
those
yeah.
are fine.
So in this picture, we take the A's and B's and we just switch them. And so the thing that you don't notice when you do this is that you have to also fix the indexes.
Yeah, but I mean, when you think about just connectivity or connectivity in graphs, because all that matters is the path between triples of nodes and what the constant on them.
Yeah. So
You don't have to worry.
so we also need to do what Avi said. If we want to switch, say, A and C, then we need to bring C down to put A up. And yeah, but it all works out either way. Okay, the other important claim, which is even more important, okay, so we have a concept of tensor product for tensors. I guess that here tensor and tensor, you should think of them as different instantiations of the word tensor. So what is the tensor product of tensors? T1 and T2. So T is given by so T is the position I1, I2, J1, J2, and K1, K2 is T1, I1, J1, K1 times T2, I2, J2, K2. So this is a oh, sorry. So this is the same, this is called the Kronecker product for matrices. And it has a very nice algebraic meaning, which you can think about. But it's just, so for matrices, the picture that people always have is you take one matrix and then you replace each entry by a scaled copy of the other matrix. Okay, and so why did we do that?
And also here the same picture box.
Yeah, yeah.
We had to divide
That's
the
right.
three-dimensional box scaled.
Yeah, and this is, by the way, this is the way that the algorithm, the Strassen algorithm works. You look at some tensor products. And so what happens when we multiply two matrix multiplication tensors? So now we can juggle the indexes, and I'm sure you can convince yourselves, and if not, then I try to convince you that you get this thing. Yeah. So this is, again, this just shuffling the indexes around. Or there's probably a better mental picture, but if you don't like mental pictures and you just want to be convinced, then so here you have AIK, BKJ, CJI, so now you'll have A, I1, K1, I2, K2, C, K2, J2, and so on, and it will just work out. Okay, and the other thing, so if T1 and T2 are rank 1 tensors, then so is T1 times T2. So why is that? So we take sum of alpha I1 xi, sum of beta I1 yi, sum of gamma, well, maybe we'll this way. Yeah, this works also for matrices or for any other order. So now we take the tensor product with sum of capital I. Oh, let's do j's here. Okay, and this is equal to sum of alpha I, aj, xij, and so on. Okay, so you can see that we just get another rank 1 tensor. Okay, is this convincing?
How do you define a rank 1 tensor?
Oh, it's something of this form.
One just has to remember that the new basis is xij.
Yeah, yeah. That's true. Not writing anything. So what we get is that the rank of the tensor product of two tensors is at most the product of their rank. And in general, we don't expect equality here, I should say. So it'll be very surprising. Okay? Now, one thing that this gives us, so far we saw if there was a way to multiply two n by n matrices, it gave us some bound on omega. But actually, it doesn't have to be the n tensor. So suppose that we know that the rank of NMP is at most some rho. And also the rank of MNP is most some rho. And the rank of PNN is at most rho. So the rank of NMP, NMP, NMP is most rho cubed. And so NMP to the omega is at most rho cubed. Okay, what this gives us yeah, and we'll see next week the Coppersmith-Winograd identity is about computing inner products. So it's 1 something 1.
Of different n and p, right?
No, so an inner product is when n and p are 1.
Oh, yeah.
And this is already really useful, even though you think inner product is like trivial. So it's several inner products. So now we get that NMP to the omega over 3 is at most the rank of NMP. And this is sometimes known as tau. Yeah, so this is the second in our sequence of identities on omega. Yeah, so questions on this? Yeah.
Just a small terminology thing. So it's probably best not to call it as a tensor product, but a canonical product. I think like if you think of it as an operator,
Yeah.
and then the tensor product of the operator spaces, you have to do some other construction for norms to carry through. So it's,
No, I think it should be the same thing. You just collapse them.
don't know how you view it as a.
Yeah. But the canonical product and the tensor product is the same thing, and usually this is called tensor product. It's confusing in this, so maybe we shouldn't call them tensors, these matrices. Call them hyphen matrices. Okay, so after the break, let's see, so we got all the way down to here. So we only have 3 different things to do after the break. So now let's take a 7-minute break.
מה ליבדתי אותך משהו כאן?
כן.
מה זה x ו-y?
הם משתנים פורמליים.
מה זה d?
D זה מטריצה. אנחנו חושבים...
זה אפילו עוזר, זה לא כמו...
כן, לא, אז אני מניחה שנותנים שזה עוזר.
איך משהו זה מפתיע בהתחלה שרואים את זה.
Okay, so shall I start? Okay, so now we're going to describe some really strange phenomenon. So here we have a 2 by 2 by 2 tensor. Okay, so I write it as 2 slices of a matrix. Okay, and the claim is that it has rank 3. Now, I read it in some presentation, so I don't know how they proved it, but you can prove it using Grevno basis. Just write the combination, and you see that there's no solution of rank 2. But if you add here some small epsilon, then you can check that both of these are rank 1 tensors. So you can write it as a linear combination of only 2 rank 1 tensors. And we can put this inside the tensors if you want. So maybe it's better to do it this way. Yeah. So now it gives you a decomposition of rank 2. So this tensor, which is very close to this tensor, is only rank 2, even though this thing is rank 3. So there is some sequence of tensors approaching the original tensor, which has a smaller rank than the actual tensor. Now, this is something that cannot happen for matrices.
I'm sorry, why does the top tensor has a rank 3?
Well, you have to prove it, but you understand that it's 2 matrices on top of each other. There are 3 ones, and there is no way to compare the two.
Okay, I'm sorry, maybe I don't get what's written here.
It's actually 2 by 2 by 2 matrix.
Okay.
2 by 2 by 2 tensor, which has these 3 ones in it.
Yeah.
Oh, okay. So I interpreted it just as the product of 2 matrices.
No.
It's like this layer and then that layer.
Yeah,
Okay.
yeah. I'm not claiming to have proven that this actually has tensor rank 3. I don't know if it's true, but it was claimed, and let's hope it's true. But it's a limit of rank 2 tensors. Okay, so why can't this happen for matrices? So we know that the rank of a matrix, so if a matrix has rank n minus 1, then it means that its determinant vanishes. Okay, it has rank n minus 2 if the last 2 coefficients in the characteristic polynomial vanish. Okay, so the rank is defined by these some polynomials vanishing. And these polynomials, they're all given by some deterministal formulas, so they're all polynomials in the entries of the matrix. And in particular, they are continuous functions. Okay, so if you have if you have your matrix and it's a limit of matrices of rank 10, then it means that all these coefficients vanish for all these matrices, and because these coefficients are continuous, then your matrix actually also has rank at most 10. Okay, but for these tensors, we don't have a characteristic polynomial. So this doesn't work, and indeed, it's not the case. It's very surprising. Now for something even more surprising.
Right here in the formula, the second
Yeah.
one is just a plus 1, right?
Sorry.
Oh, yeah, here it's
Yeah. Right, and then you're right. Yeah. Okay, so here's something even more surprising.
You cannot go by more than 1.
I'm not sure.
Right, not 2.
Okay, so definition. So the border rank of a tensor T is the minimal law such that T is the limit of rank T tensors. Okay, and now there's a theorem. So suppose the border rank of T is law, then there is a tensor T epsilon over your field, let's say the complex numbers, so everything here is complex, or the polynomial ring over the complex numbers, such that the rank of T epsilon is law, and here the rank is over the field with epsilon. Oh, right, and if you substitute 0, then you get T. Okay, so what is this thing saying? It's just saying what's written here. So here we had some tensor which had border rank 2. So there's a way to add some epsilons to the matrix in some polynomial fashion. So this is this example. Now the new thing has actually smaller rank. And when you do the rank decomposition, you can also use negative powers of epsilon. Okay, so that's all that this thing is saying.
So why is this a theorem and not a definition of?
No, this is the definition of. So nobody said that the way that these tensors approach that tensor is in this polynomial fashion. And nobody said that there is some uniform way of writing this decomposition. Okay, but that's
So these are Lorentz series and epsilon, or these are polynomials and epsilon?
no, it's so here it's polynomials in epsilon, and here
You
it's
have the rational function of epsilon.
yeah, no. So this is just for the rank decomposition. So for the rank decomposition, it's yeah, fractions, and
What does it mean to use negative powers of epsilon if you don't want to set epsilon equals 0?
oh, so I'm setting epsilon.
You set it only in the tensor, not in the decomposition.
Oh, I see.
Yeah.
There, epsilon appears positively on it.
Yeah.
So the left-hand side is a polynomial in epsilon, but the split gives you
Yeah, right.
something with negative powers.
Right.
So is the definition of border rank dependent on the field?
Yeah.
For every field,
Sure.
there is a border, like that.
Yeah.
And is there some multiplicity that goes by? Oh, yeah, sure.
Well, yeah, if you go to yeah, sure. Yeah. But we're not worrying about fields which are not the real numbers of the complex numbers. Okay, so this is apparently lemma 2.33 in Mumford's is, what was it? Algebraic geometry 1, projective varieties. Yeah. The proof looks pretty simple. Unfortunately, I can't understand anything there. But it's on page 30.
Much more general than we said.
Yeah, yeah.
Talking about closure of varieties.
Yeah, so and so this 2.33, which is on page 38, so it can't be too difficult. It only talks about algebraic closed fields, and it's actually true in more generality. We're using a different argument. So if you're interested in this, then talk to me, and I'll give you the book, and you can read all about it and explain it to me. Of course, for us, it doesn't matter because you could have defined border rank this way. But it's nice that it's actually the same as this definition. Yeah. Okay, so you can think of it as, so suppose we had this sort of identity for matrix multiplication, then one way you could use it is you could use it to compute matrix multiplication approximately, because you will put this very small epsilon, and then it will give you an approximation for the actual product. Okay, so that's why these things used to be called approximate identities or whatever. But actually, we will show that we can get rid of this, and we can compute it exactly, even though there are these epsilons. So now it's time to look at number 2 in your handout. Okay, so this is some identity found by, or appearing in a paper by 4 Italian authors, one of them being Bini. Yeah, and if you put 2 copies of this identity, then it shows that the border rank of 3, 2, 2 is at most 10. Okay, now if you look at the identity, then there are no negative powers of epsilon anywhere, but to compensate, then the matrix we start with, it has a leading coefficient of epsilon. So we really have epsilon times 3, 2, 2 plus terms with higher powers of epsilon. This is equal to some rank decomposition, where here there are no negative powers of epsilon, but they can be constant coefficients. Okay, and so if this behaved the same way as the usual rank, then we would get that, so here NMP is 12. So 12 to the omega over 3 is at most 10. And the question is whether we can say the same thing, even though it's only border rank here. Okay, so that's what we're going to show now, and this is a general phenomenon. And this is, again, this power series trick that is going to repeat itself all over and again. Right, so what you're going to do is you're going to take some high tensor power n, and tensor this identity with itself n times. Okay, so it's going to be epsilon to the n times 3 to the n, 2 to the n, 2 to the n. And this is going to be the sum of 10 to the n factors, rank 1 tensors. And each of them is some complicated polynomial in epsilon. But we're actually only interested in the coefficient of epsilon to the n. Okay, so let's take one of these factors. So it's only one of them. And it's so it's alpha of epsilon times beta of epsilon times gamma of epsilon. Okay, so we can think of each of these alpha, beta, and gamma as some polynomials in epsilon. Okay, and we are interested. We want the coefficient of epsilon to the n of this expression. Okay, so how many products does it take us to compute this coefficient without the epsilon? Yeah, and sort of n squared. So yeah, using n to the 3 minus 1. We can compute this coefficient. Okay, so this shows.
Capital N, right?
Hmm?
It's not small n.
Right. Okay, so the rank of 3 to the n, 2 to the n, 2 to the n is at most order n squared times 10 to the n. Okay, so now 12 to the n omega over 3 is at most order n squared 10 to the n. So now you take n really large and take the nth root and take the limit, and you get that 12 to the power omega over 3 is at most 10, which is what we wanted to get. Okay, so this shows that the fact that there is bordering here rather than rank, it doesn't make a big difference. We can always fix it.
Does it work on smaller field?
Does it work in a smaller field? So I don't think the
have even, comparing the size of epsilon squared is meaningless.
yeah, no, you're doing everything formally. You can think of epsilon as an infinitesimal, but you don't have to.
So it works.
Yeah. Yeah, and you can always do that. Yeah, so more generally, so nmp to the omega over 3 is always at most the border rank of nmp. Yeah.
So we go to the capital N size to absorb that n squared factor, but can you remind me
Right.
where that comes from?
Yeah, so this n squared factor comes from, you want to extract the coefficient of epsilon to the n in this in each of these products. So we have a sum here of 10 to the n rank 1 tensors. And these are just products of some polynomials in epsilon. And we want to get rid of epsilon. So we only want to look at the coefficient of epsilon to the capital N. And you can do it because you can just multiply the polynomials and look at the coefficient of epsilon to the n. So you get the sum of order n squared terms, or you can, it's n choose something, or n plus something choose 2.
So if you can do everything formally, then it's field independent, right?
Yeah, this argument is, yeah.
So border rank actually is field independent.
No, because it's defined in terms of the rank decomposition.
Its value depends on the field.
Yeah, this argument. Yeah, so if you want to multiply matrices over a given field, then you need to use the same field when you do border rank. That's all. So the field only matters because you can use coefficients. The coefficients, the constants, which didn't actually come up so far, and not going to come up also, they come from some field. So maybe if you could use pi, then it would make a big difference. You could use I. Okay. Okay, so now we're advancing fast. Now we can look at identity 3 in your handout. Yeah, so one of the heroes of the field, other than Strassen, is Schoenhager. And Schoenhager had this way of coming up with all these identities. This is really the mystery in the field.
Very impressive to hear it pronounced correctly, too.
Schoenhager, yeah. Yeah, so what Schoenhager gives us is this identity. It shows that okay, so I'll explain what this plus with a circle means, if you haven't guessed it already. Right. So what this direct sum sign mean? So we have here two tensors, and they're going to be over disjoint variables. Okay, so this means that we can compute an outer product of for a 4 by 1 vector by 1 by 4 vector, and an inner product using only 17 essential multiplications. And that is sort of surprising because the rank of this tensor is 16. Yeah, if you want to compute this outer product, you clearly need to do 16 multiplications. And now if I add only one multiplication, I can suddenly compute this inner product of length 9. Very surprising. Okay, and now we want to use this thing to multiply square matrices. And the way we do it, so there'll be some general argument, and it will give us another formula which generalizes these formulas. This is known as the asymptotic sum inequality, or the Schoenhager tau theorem. Okay, so we'll do it in several steps. So step 1, suppose So I'm going to completely forget about this thing being a border rank. We do everything over rank, and you can fix everything. So suppose that the rank of C multiplications of site n by n is at most O. So how can you use it to multiply matrices? So I want to say that it's morally as if the rank of one multiplication is rho over C. So nobody asked, but this means C disjoint copies of this n and n. Okay, and so n to the omega is at most rho over C. Yeah, so what I'm claiming, I'll explain why it's true, is that we can sort of amortize these multiplications. So what this says is that on the average, you can multiply an n by n matrix using rho over C essential multiplications. Yeah, and the way to do it, so
So it's a culminating of C times the.
yeah. So it's the disjoint sum of C copies of n and n. It doesn't matter. Disjoint sum just means that it's disjoint variables.
So it's the sum operation of let's say.
Yeah. Right. So. Okay, so you can imagine this Strassen algorithm. It starts by splitting the matrix into so this is your original matrix, and then we split it into 7, and then we split it into 7 more, and so on. Now, if there was a way to somehow, say, multiply 2 of them using less than what you'd expect, then you could group these multiplications in 2s. But because 7 is not even, so it will be like this, then you'll lose something. In your amortized algorithm, you won't be able to do it exactly to use it to its fullest extent. But if you do one more level, then you'll do better. Then so it's still odd, but now you'll have 49, and you'll only be losing one of them. Yeah, so you can imagine we do it to some reasonable depth, and then you can amortize as close as you want to the optimum. Okay, and you can carry this argument formally, but I won't do it. So this argument should convince you that if you can multiply C disjoint n by n matrices using amortized rho, so amortized rho over C, then you get this bound on omega. Okay, so this was step 1. Step 2 is very similar. So now we suppose that the rank of C copies of NMP is most rho. Then I want to say that NMP to the omega over 3 is at most over C. And we already saw how to do this. You just rotate and multiply, and everything works out. Okay, so now we get to the interesting step. I think you need to go, Avi.
That's waiting for you to write it down.
So here's the idea. So we're going to take some high tensor power. Okay, so going to now we are back to this identity, and we will forget about this border stuff. So we take a high tensor power, and this is what we get. Okay, and now we're going to isolate one of these terms and just apply the bound that we wrote there. Okay, so for a given I, the bound that we're going to get is that so 4 to the I and minus I, and 4 to the I to the omega over 3 is at most 17 to the n over, well, let's do it this way. So this is the bound that we're going to get for any specific I that we choose, and we just need to optimize over I. Now there's something nice going on here. So what is the sum of all these terms? So the sum of all these terms so it's just right. Okay. So this is, you can check it. It's just some formal identity. So what this tells us is that for some I, then this thing is at least an n+1 fraction of this thing, right? So for some I, we can actually compute the I, but it doesn't matter. For some I, this thing is at least 16 to the omega over 3 plus 9 to the omega over 3 to the n over n plus 1. Actually, you can get square root n, but it doesn't matter. I'm saying n plus 1 because there are n plus 1 choices for I. Okay, so we choose this I, and what we get is that 16 to the omega over 3 plus 9 to the omega over 3 to the n over n plus 1 is at most 17 to the n. Okay, so now you take nth root and take tend n to infinity, and we get that 16 to the omega over 3 plus 9 to the omega over 3 is at most 17. And you can see this is a generalization of what we had before, of all the bounds we had before. Okay, is this convincing? So the idea was we take this high tensor power and we focus on one specific type of tensors occurring. And it's okay to focus on only one of them because there are only polynomially many of them. So in the limit, we don't actually lose anything. This was the idea, and it's going to recur next week. Okay, and more generally, you can state the full theorem. So this is the asymptotic sum inequality. So let's see, sum of ni, mi, pi to the omega over 3 is at most the border rank so this is the general form. But it's just the same thing as we were doing. The only difference is that instead of n, you might get more terms because you have more types. But it's still going to be some polynomial as long as this sum is finite. And it's also called the tau theorem. If you replace omega over 3 with tau, then you have tau in the theorem. Okay. So yeah, so Schoenhager's identity is somewhat surprising because you had this identity, trivial identity for well, this one, and you improved it into this identity. Now, if you apply the asymptotic sum inequality to this identity, then you probably get omega equals 3 or something. You got something, and you can get a better bound by adding this inner product. And Coppersmith-Winograd showed that you can always do it. So if you have any kind of tensor which is a direct sum of matrix product tensors, then you can always add some inner products in a way which will give you a better bound in the asymptotic sum inequality. So that means that if the bound that you get uses the asymptotic sum inequality, then you're not going to get the minimal value of omega if there's anything like this. There's always a way to improve it further. And next week we'll see that some sort of way around it, because we're going to apply it for more and more complicated tensors.
So if you push this to the extreme and keep doing that, what you get to be short?
No.
Start with a certain bound, and then suppose you keep doing this addition and running the.
Yeah, so the improvement is probably very slight.
No, it just. I was just curious about the general form. You got something, right? So how far down can you bring it after this process? Iterate it infinitely.
Yeah, I don't think they considered it. So it's very similar to what we have in the Coppersmith-Winograd type algorithms for matrix multiplication, where you can take the square of the identity, then the fourth power, and you get diminishing returns. Yeah, it's a similar idea. For the Coppersmith-Winograd algorithms, there might be a way to calculate the limit. Here, it's not so clear, but
Because it's such a natural thing to do.
yeah, but you can, the parameters are pretty explicit, and you can probably come up with some bound on what it can possibly give you, and at least show that you can't get omega equals 2 this way. Yeah, but they don't do it. Yeah.
So I guess we try to let computers come up with those identities.
I have no idea how people come up with identities. That's mysterious.
How about trying the computer for that?
Yeah, and that's great. I think that's the best venue to improve the omega, finding a better identity.
There were some papers that used computer search for GMA.
No, well, we get to this next week. They use the same basic identity from 86.
What, the 414 thing.
Yeah.
I mean, can't you use computer to come up with?
Yeah, if you can do it, then great. Yeah.
Yes.
Yeah, I think that's the best way to get improved bounds on omega. Since 86, no better identity has been known, so apparently it's not so easy, or 87, I don't remember. We'll get to it next week. So what happens in the Coppersmith-Winograd papers, you start with some basic identity, and then you get a new identity by tensoring it many times and zeroing the variables.
So what I thought that you done in the research was looking at higher sensitivity.
Yeah.
But it's not new,
No.
but you're still doing analysis of this higher order.
You have to solve some optimization problems, but you don't come up with new identities. We'll see it next week. Okay, so now I'm going to quickly show you how to do rectangular matrix multiplication. Okay, and then we can finish. Okay, so the goal in rectangular matrix multiplication is to multiply. So the picture is like this. You want to compute this matrix product, where this index, so this is n, and this is n to the alpha. And you want to do it in n to the 2 plus epsilon. You want to push alpha as large as possible. So if omega equals 2, it's the same as alpha equaling 1. Okay, in some cases, you can get, for some values of alpha, a complexity of O tilde n squared. So you don't have the epsilon. Instead, you have logarithmic factors, but that's not what I'm going to show. Okay, so we're just going to show omega plus epsilon, although the epsilon, you won't even see it because we're doing it quickly. Okay, so we start with the same identity by Schoenhager, only with different parameters. So we choose these different parameters. There's some optimization going on here. So for anything you put here and for anything you put here, there's something that you put here, and it's the same sort of identity, and this is just the best that you can do. Okay, and now the approach is very similar, only we're not going to symmetrize. So we're going to take some high tensor power of this identity. And now we're going to choose some value of I and ignore all the rest. Okay. And when we do that, then what we will get is that, morally speaking, the rank of this tensor is at most 10 to the n over n choose i's. And this, morally speaking, means that you can get some algorithm and so on. Now, in order to get n squared, we want this thing to be equal to roughly to 9 to the I. Okay, so in order to get a rank of roughly n squared, we need 10 to the n over n choose I to be roughly 9 to the I. So 10 to the n is roughly ni 9 to the I. Okay, and we already know that we can achieve this by choosing the highest or the best I, because if you sum this over all I, you get 10 to the n, so you can get almost to 10 to the n. But here we also need to know the exact value of I, so the best value of I is 0.9n. Okay, and then what we get is that roughly, so this is 3 to the 0.9n, 4 to the 0.1n, and 3 to the 0.9n is roughly at most 9 to the 9n. Okay, and then you just have to put, if this is n, then this is n to the alpha, where you can compute alpha. Alpha is some constant. Okay, so this is the idea. I'm skipping some details, but the idea is that you take this, basically the same identity, and you, again, take some high tensor power. And now we're going to isolate some factor, and everything is just going to work. And we're going to choose the factors such that the number of, the rank is roughly n squared. And the price we have to pay is that now it's not square multiplication, but rectangular multiplication. So here there's a sum, and we isolate just one of them. Yeah. So that's all. It's pretty simple. For some technical reason that you don't see here, this doesn't actually give O tilde of n squared. There's something slightly different which you can do and does give O tilde of n squared. But it is this thing that generalizes. So that's how I present this. OK, so any questions about this? OK, so I'll just tell you what to expect next week. So the asymptotic sum inequality enters the question. Suppose that I have an identity of this form. So I have a direct sum of matrix product tensors, and its border rank is most something. What does it tell me about omega? And next week, we'll have a sum. So the tensors will not be disjoint. The variables will not be disjoint. So we will need to somehow make them disjoint. And this is this crazy construction with sum free sets and Sadin-Spencer sets and all of this mess. So that's next week. So any questions for this week?